Introduction to drone technology. Drone technology, formerly known as Unmanned Aerial Systems, UAS, represents a significant leap in aviation, offering versatile capabilities across numerous sectors. These remotely piloted or autonomously operated aircraft are equipped with advanced sensors, cameras, and communication systems, enabling them to perform tasks that are often hazardous, impractical, or costly for manned aircraft. The proliferation of drones has democratized aerial perspectives and data collection, transforming industries from agriculture to entertainment. Understanding the fundamental concepts of drone technology is crucial for anyone looking to enter this dynamic field. This course will provide a comprehensive overview, starting with the basics and progressing to specialized applications and regulatory considerations. Drones are essentially flying robots, ranging in size from small, palm-sized devices to large, sophisticated aircraft capable of carrying heavy payloads over long distances. Their core functionality relies on a combination of aerodynamics, propulsion, navigation, and control systems. The ability to operate without a human pilot on board allows for greater endurance, access to difficult terrains, and reduced risk to human life in dangerous environments. As technology continues to advance, drones are becoming more intelligent, efficient, and integrated into daily operations, promising even greater impact in the years to come. History and evolution of drones. The concept of unmanned aerial vehicles dates back over a century, with early prototypes emerging during World War I as aerial torpedoes and target practice aircraft. These rudimentary drones were primarily used for military purposes, evolving slowly through the interwar period and significantly during World War II with the development of radio-controlled aircraft. Post-war, research continued into surveillance and reconnaissance drones, pushing the boundaries of remote control and autonomous flight. The early designs were often bulky and unreliable, requiring significant human intervention for operation and navigation. A major turning point arrived in the late 20th and early 21st centuries with advancements in microelectronics, GPS technology, and battery efficiency. These innovations allowed for the miniaturization of components and the development of more sophisticated flight control systems, paving the way for the modern drone era. Initially still military-focused, drones like the Predator and Reaper gained prominence for surveillance and combat roles. Subsequently, their capabilities expanded into civilian applications driven by hobbyists and commercial enterprises, leading to the diverse range of drones available today. This rapid evolution continues to shape their design and functionality. Types of drones. Rotary wing. Rotary wing drones, commonly known as multi-rotors, are characterized by their ability to take off and land vertically, hover in place, and maneuver with exceptional agility. These drones achieve flight through the use of multiple propellers, typically 4 quadcopters, 6 hexacopters, or 8 octocopters, each driven by an independent motor. The varying speeds of these motors allow for precise control over pitch, roll, yaw, and altitude. This design makes them ideal for tasks requiring stable hovering, close-range inspection, and high-quality aerial photography or videography. Their ease of operation and relatively stable flight characteristics have made them popular among hobbyists and commercial operators alike. The primary advantages of rotary wing drones include their compact size, maneuverability in confined spaces, and the ability to carry diverse payloads for short to medium durations. However, their efficiency is generally lower than fixed-wing drones, leading to shorter flight times, especially with heavier payloads. Despite this limitation, ongoing advancements in battery technology and motor efficiency are continuously improving their endurance. Common applications for multi-rotors include aerial surveying of small areas, real estate photography, package delivery in urban environments, and search and rescue operations, where precise hovering is critical. Types of drones: fixed-wing and hybrid. Fixed-wing drones resemble traditional airplanes, utilizing a wing to generate lift, and a propeller or jet engine for forward thrust. Unlike rotary-wing drones, they cannot hover in place and require a runway or catapult for takeoff and a runway or parachute for landing. Their design prioritizes aerodynamic efficiency, allowing for significantly longer flight times and greater range compared to multi-rotors. Especially when covering large geographical areas, this makes them highly suitable for extensive mapping, long-range surveillance, and environmental monitoring tasks where endurance is a key requirement. Fixed-wing drones are less agile but excel in sustained flight. Hybrid drones, also known as vertical takeoff and landing (VTOL), fixed-wing drones, combine the best features of both rotary-wing and fixed-wing designs. They can take off and land vertically like a multi-rotor, eliminating the need for a runway, and then transition to forward flight using a wing for efficient, long-duration missions. This versatility makes them incredibly valuable for operations in remote areas or locations without suitable landing strips. VTOL drones offer an excellent balance of operational flexibility, endurance, and payload capacity, making them increasingly popular for diverse commercial and industrial applications. Their complexity is higher, but the benefits often outweigh this. Drone components, airframe and motors. The airframe is the structural skeleton of a drone, providing the foundation upon which all other components are mounted. It determines the drone's overall shape, size, and weight, significantly influencing its aerodynamic performance and payload capacity. Airframes are typically constructed from lightweight yet durable materials, such as carbon fiber, aluminum, or specialized plastics, to maximize flight efficiency and resistance to impact. The design of the airframe also dictates the placement of motors, batteries, and sensors, ensuring optimal weight distribution and structural integrity. A well-designed airframe is crucial for stable flight and protection of internal electronics. Motors are the heart of a drone's propulsion system, converting electrical energy from the battery into mechanical energy to spin the propellers. Most modern drones utilize brushless DC (BLDC) motors, which are highly efficient, durable, and offer precise control over rotational speed. The size and power of the motors must be carefully matched to the drone's weight, propeller size, and intended payload to ensure adequate thrust for stable flight. Each motor is controlled independently by the flight controller, allowing for the precise adjustments necessary for hovering, maneuvering, and maintaining altitude. The quality and synchronization of these motors are paramount for reliable drone performance. Drone components, propellers and batteries. Propellers are critical for generating the lift and thrust required for drone flight. They are essentially rotating wings, designed to push air downwards, creating an upward force that counteracts gravity. The size, pitch, and number of blades on a propeller significantly impact the drone's flight characteristics, including thrust, efficiency, and noise levels. Propellers are typically made from lightweight yet rigid materials like plastic, carbon fiber, or wood, chosen for their balance of strength and weight. Damage to even a single propeller can severely compromise flight stability and safety, necessitating regular inspection and replacement. Proper propeller selection is vital for optimal performance. Batteries serve as the power source for all drone components, from motors to flight controllers and payloads. Lithium polymer (LiPo) batteries are the most common type used in drones due to their high energy density, providing a significant amount of power relative to their weight. The capacity, mAh, and voltage S rating of a LiPo battery determine the drone's flight time and power output. Proper battery management, including charging, discharging, and storage practices, is essential for maximizing battery life, ensuring safety, and preventing damage. Battery technology is a key area of ongoing research, with continuous efforts to improve energy density and reduce charging times. Drone components, flight controller, and GPS. The flight controller (FC) is the brain of the drone, an onboard computer responsible for interpreting pilot commands, processing sensor data, and sending instructions to the motors to maintain stable flight. It continuously monitors the drone's orientation altitude, and position, making thousands of micro-adjustments per second to keep the aircraft stable and responsive. Modern flight controllers are highly sophisticated, often running complex algorithms and firmware that can be customized for different drone types and flight characteristics. They are central to the drone's autonomous capabilities and overall performance, ensuring smooth and controlled movements. Global Positioning System (GPS) modules are integral to modern drone navigation, providing precise location data that allows the flight controller to understand the drone's position in 3D space. GPS enables features such as position hold, waypoint navigation, return-to-home functionality, and autonomous flight paths, significantly enhancing operational capabilities and safety. While GPS is highly reliable in open environments, its accuracy can be affected by obstructions like tall buildings or dense foliage, or by signal interference. Advanced drones often integrate other navigation systems, such as GLONASS or Galileo, and even visual positioning systems to augment GPS data and improve positional accuracy and reliability in challenging conditions. Drone components, sensors, and payloads. Drones are equipped with a variety of sensors that collect crucial data about their environment and operational status. Beyond GPS, common sensors include accelerometers and gyroscopes for measuring orientation and angular velocity, barometers for altitude sensing, and magnetometers for heading information. More advanced drones may feature ultrasonic or optical flow sensors for precise indoor positioning, obstacle avoidance sensors, for example, LiDAR, stereo vision for enhanced safety, and thermal cameras for specialized applications. These sensors provide the flight controller with a comprehensive understanding of the drone's state and surroundings, enabling intelligent flight decisions and data collection. The integration of these sensors is vital for robust performance. Payloads refer to the equipment or cargo that a drone carries to perform its mission. The type of payload depends entirely on the drone's intended application. Common payloads include high-resolution cameras for photography and videography, multispectral or thermal cameras for agricultural or inspection purposes, LiDAR scanners for 3D mapping, and even delivery boxes for logistics. The drone's design, motor power, and battery capacity must be sufficient to lift and operate the chosen payload effectively without compromising flight performance or safety. The ability to swap out different payloads makes drones incredibly versatile tools for a wide array of tasks across various industries. Principles of flight. Aerodynamics. Aerodynamics is the science that governs how air interacts with moving objects, and it is fundamental to understanding how drones fly. For fixed-wing drones, the shape of the wings, airfoils, is designed to create lift, an upward force that opposes gravity, as air flows over and under them. The difference in air pressure above and below the wing generates this lift. Thrust, provided by propellers or jet engines, propels the drone forward. Overcoming drag, which is the resistance caused by air friction. Understanding these forces, lift, thrust, drag, and weight, is crucial for efficient and stable flight. The design of the drone's body also minimizes drag. For rotary-wing drones, aerodynamics is applied differently. Each rotating propeller acts as a small wing, generating lift by pushing air downwards. The collective thrust from all propellers must be greater than the drone's weight for it to ascend. By independently controlling the speed of each motor, the flight controller can manipulate the thrust generated by individual propellers, thereby controlling the drone's pitch, roll, and yaw. This precise control over aerodynamic forces allows multi-rotors to hover, move in any direction, and perform complex maneuvers with remarkable agility. The efficiency of the propeller design directly impacts flight duration and stability. Principles of flight. Stability and control. Stability refers to a drone's ability to return to its original flight path or attitude after being disturbed by external forces like wind gusts. Drones achieve stability through a combination of aerodynamic design and sophisticated electronic flight control systems. Static stability means the drone naturally tends to return to equilibrium, while dynamic stability involves oscillations that eventually dampen out. Modern flight controllers use sensor data from gyroscopes and accelerometers to detect deviations from the desired flight path and automatically make corrections to the motor speeds, ensuring a smooth and stable flight experience. This continuous feedback loop is essential for precise control. Control involves the pilot's ability to intentionally change the drone's attitude and trajectory. For rotary-wing drones, control inputs from the remote controller are translated by the flight controller into differential changes in motor speeds. For example, increasing the speed of propellers on one side while decreasing it on the other causes the drone to roll. Similarly, adjusting front and rear motor speeds controls pitch, and varying speeds diagonally controls yaw. Fixed-wing drones use control surfaces like ailerons, elevators, and rudders, similar to manned aircraft, to manipulate airflow and change direction. Mastering these control principles is fundamental for safe and effective drone operation, allowing for intricate maneuvers and precise positioning during missions. Drone operation. Pre-flight checks. Before every drone flight, a thorough pre-flight check is absolutely essential to ensure safety, compliance, and mission success. This systematic inspection helps identify any potential issues that could lead to equipment failure or an accident during operation. Key steps include visually inspecting the drone's airframe for any damage, cracks, or loose components, and ensuring all propellers are securely attached and free from nicks or bends. It is crucial to verify that the landing gear is functional and properly extended, and that all wiring connections are secure. Neglecting these checks can have serious consequences, impacting both the drone and public safety. Beyond physical inspection, pre-flight checks also involve verifying the drone's electronic systems. This includes checking battery levels for both the drone and the remote controller, ensuring they are adequately charged for the planned flight duration. Operators must confirm that the flight controller firmware is up to date and that GPS signal acquisition is strong and accurate. Furthermore, it is important to review the flight plan, check weather conditions, assess the operational area for hazards, and ensure compliance with local airspace regulations. A comprehensive pre-flight checklist minimizes risks and maximizes the likelihood of a successful and safe drone mission. Drone operation, takeoff and landing. Executing a smooth and controlled takeoff is a fundamental skill for any drone pilot. Before initiating takeoff, the drone should be placed on a flat, clear surface, away from obstacles and people. The pilot must ensure all systems are green, including GPS lock and sufficient battery. For multi-rotors, takeoff typically involves slowly increasing throttle until the drone achieves a stable hover a few feet off the ground, allowing for immediate observation of any anomalies. Fixed-wing drones may require a hand launch, catapult, or a short runway, gaining speed until sufficient lift is generated. A controlled ascent is critical to avoid sudden movements or loss of control, ensuring a safe start to the mission. Landing a drone safely requires precision and careful judgment. For multi-rotors, the pilot should slowly descend, maintaining visual line of sight and adjusting for wind conditions. A gentle touchdown on the designated landing zone is ideal, followed by immediately cutting the motors once the drone is firmly on the ground. Fixed-wing drones often perform a gliding approach, landing on a runway or in an open area, sometimes utilizing a parachute for controlled descent. In emergency situations, drones are often programmed with an automatic return-to-home (RTH) function, which guides the drone back to its takeoff point and initiates an autonomous landing. Practicing these maneuvers repeatedly builds confidence and proficiency, minimizing risks during real-world operations. Drone operation. In-flight maneuvers. Once airborne, drone pilots must master a range of in-flight maneuvers to effectively complete their missions. Basic maneuvers include maintaining a stable hover, flying forward, backward, left and right, and performing controlled ascents and descents. These movements require precise coordination of throttle, pitch, roll, and yaw controls. For example, a forward movement is achieved by pitching the drone slightly forward and increasing throttle, while a turn involves a combination of roll and yaw. Smooth transitions between these movements are crucial for capturing stable footage or navigating complex environments. Proficiency in these basic controls forms the foundation for more advanced operations. Advanced in-flight maneuvers often involve executing predefined flight paths, orbiting points of interest, or performing complex aerial patterns for mapping and inspection. Many modern drones offer intelligent flight modes, such as Follow Me, Waypoint Navigation, or Orbit, which automate these complex movements, allowing the pilot to focus on data collection. However, even with automation, the pilot must be prepared to take manual control at any moment, especially in dynamic conditions or emergencies. Understanding the drone's capabilities and limitations, coupled with extensive practice, enables pilots to perform intricate maneuvers safely and efficiently, maximizing the utility of their drone for specialized tasks. Safety protocols and best practices. Operating drones safely is paramount, requiring strict adherence to established protocols and best practices to prevent accidents, protect property, and ensure public safety. A fundamental rule is to always maintain visual line of sight (VLOS) with the drone, unless operating under specific waivers or regulations that permit beyond visual line of sight (BVLOS) operations. This ensures the pilot can react immediately to any unforeseen circumstances. It is also crucial to avoid flying over crowds of people, near airports, or in restricted airspace without proper authorization. Thorough pre-flight checks, as previously discussed, are a cornerstone of safe operation, identifying potential issues before they become critical during flight. Additional best practices include regularly maintaining the drone and its components, ensuring software and firmware are updated, and using reliable, fully charged batteries. Pilots should always be aware of their surroundings, monitoring weather conditions, wind speed, and potential obstacles like power lines or trees. Having a contingency plan for emergencies, such as a designated landing zone or a return-to-home failsafe, is also vital. Furthermore, respecting privacy concerns and local regulations regarding drone use is essential for responsible operation. Adopting a safety-first mindset and continuous training are key to mitigating risks and fostering a positive public perception of drone technology. Regulatory frameworks, airspace restrictions. Drone operations are subject to strict regulatory frameworks designed to ensure aviation safety and manage airspace. One of the most critical aspects of these regulations involves airspace restrictions, which define where and how drones can fly. Airspace is categorized into different classes, for example, Class A, B, C, D, E, G, each with specific rules for manned and unmanned aircraft. Drones are generally restricted from flying in controlled airspace, classes B, C, D, E, around airports without prior authorization. This authorization often requires specific waivers or participation in systems like the Low Altitude Authorization and Notification Capability (LANC) in countries like the United States. Understanding these classifications is fundamental. Beyond controlled airspace, there are also temporary flight restrictions, TFRs, for events like sporting gatherings, wildfires, or VIP movements, which prohibit drone flights. National parks, military bases, and critical infrastructure sites often have permanent no-fly zones. Ignorance of these restrictions is not an excuse and can lead to severe penalties, including fines and imprisonment. Drone pilots must utilize up-to-date aeronautical charts, mobile applications, and official government resources to identify restricted areas before every flight. Compliance with airspace regulations is non-negotiable for safe and legal drone operations, protecting both the drone and other aircraft. Point. Regulatory frameworks, pilot certification. In many countries, operating a drone for commercial purposes requires specific pilot certification or licensing. For instance, in the United States, the the Federal Aviation Administration, FAA, mandates that commercial drone operators obtain a remote pilot certificate under Part 107 of the FAA regulations. This certification demonstrates that the pilot possesses the necessary knowledge and skills to operate a drone safely and legally within the national airspace system. The process typically involves passing an aeronautical knowledge test covering topics such as airspace classifications, weather, drone loading, emergency procedures, and regulations. This ensures a baseline level of competency and understanding. The requirements for drone pilot certification vary significantly by country and even by the weight and type of drone being operated. Some regions may have different categories for recreational versus commercial use, or for drones above a certain weight threshold. Maintaining certification often involves recurrent training or periodic knowledge tests to ensure pilots stay current with evolving regulations and best practices. Adhering to these certification requirements is not just a legal obligation, but also a professional responsibility, promoting safe and ethical drone operations. It signifies a commitment to aviation safety and professionalism within the drone industry. Data acquisition, photography and videography. Drones have revolutionized aerial photography and videography, offering unique perspectives and dynamic shots that were previously only achievable with expensive manned aircraft or cranes. High-resolution cameras, often mounted on stabilized gimbals, capture stunning stills and cinematic video footage from various altitudes and angles. The ability to fly into tight spaces or hover precisely allows for creative shots impossible from the ground. Drone photography is widely used in real estate, tourism, events, and advertising to showcase properties, landscapes, and experiences from an elevated viewpoint. The quality of the camera, lens, and gimbal stabilization are critical factors in producing professional-grade imagery. Effective drone videography requires not only technical piloting skills, but also an understanding of cinematic principles. This includes framing, composition, lighting, and smooth camera movements. Pilots often use intelligent flight modes like orbit, droney, or helix to achieve complex camera paths automatically, ensuring consistent and professional-looking footage. Post-processing software is then used to edit, color grade, and stabilize the raw footage, transforming it into polished final products. The combination of advanced drone technology and creative vision has made aerial photography and videography an accessible and powerful tool for visual storytelling, opening up new possibilities for content creators across many industries. Data acquisition. Mapping and surveying drones have become indispensable tools for mapping and surveying, offering a cost-effective and efficient alternative to traditional methods. Equipped with high-resolution cameras or LiDAR sensors, drones can quickly capture vast amounts of geospatial data over large areas. This data is then processed to create highly accurate 2D orthomosaic maps, 3D models, and digital elevation models, DEMS. Applications include topographic mapping, construction site progress monitoring, land management, and volumetric calculations for stockpiles. The speed of data collection and the ability to access difficult or dangerous terrain make drones particularly valuable in these fields. The process typically involves planning a flight path with significant image overlap to ensure comprehensive data capture. Specialized software then stitches these individual images together, correcting for distortions and creating a geo-referenced map or model. LiDAR-equipped drones can penetrate vegetation, providing accurate ground elevation data, even in densely forested areas. The precision and detail offered by drone-based mapping solutions are transforming industries that rely on accurate spatial information, from urban planning and infrastructure development to environmental conservation. This technology provides actionable insights faster and more safely than ever before. Data processing, photogrammetry basics. Photogrammetry is the science of making measurements from photographs, and it is a cornerstone of drone-based mapping and 3D modeling. The basic principle involves taking multiple overlapping images of an object or area from different perspectives. Specialized software then analyzes these images to identify common points, known as key points, and uses triangulation to determine their 3D coordinates. This process allows for the reconstruction of the scene in a three-dimensional space, creating highly accurate models and orthomosaic maps. The quality of the input images, including resolution, overlap, and lighting, directly impacts the accuracy of the final photogrammetric output. The photogrammetry workflow typically involves several stages. Image acquisition, capturing numerous overlapping photos with a drone. Image alignment, identifying common features across images to reconstruct camera positions. Dense point cloud generation, creating millions of 3D points representing the surface of the object or terrain. Mesh and texture generation, building a 3D mesh from the point cloud and applying photographic textures. Orthomosaic and DEM generation, creating a georeferenced 2D map and a digital elevation model. This sophisticated process transforms raw aerial images into actionable data, providing valuable insights for various industries. Understanding these steps is crucial for effective data utilization. Applications. Agriculture and forestry drones are transforming agriculture through precision farming techniques, allowing farmers to monitor crop health, optimize irrigation, and manage pests more efficiently. Multispectral and hyperspectral cameras mounted on drones capture data beyond the visible spectrum, revealing plant stress, nutrient deficiencies, and disease outbreaks long before they are apparent to the human eye. This information enables targeted application of water, fertilizers, and pesticides, reducing waste and improving yields. Drones can also be used for precise crop spraying, covering large areas quickly and accurately, minimizing human exposure to chemicals. This technology leads to more sustainable and productive farming practices. In forestry, drones provide invaluable tools for monitoring forest health, managing timber resources, and detecting wildfires. They can rapidly survey vast forest areas, identifying changes in tree density, species composition, and signs of disease or pest infestations. LiDAR-equipped drones can create detailed 3D models of forest canopies and underlying terrain, aiding in timber volume estimation and habitat mapping. For wildfire management, drones equipped with thermal cameras can detect hotspots, monitor fire progression, and assist firefighters in strategic planning, often operating in conditions too dangerous for manned aircraft. These applications enhance efficiency and safety in natural resource management. Applications. Inspection and infrastructure drones have revolutionized inspection and infrastructure management by providing a safer, faster, and more cost-effective method for assessing critical assets. Instead of sending human workers into dangerous or hard-to-reach locations, drones equipped with high-resolution cameras, thermal sensors, or LiDAR can collect detailed visual and thermal data. This includes inspecting bridges, power lines, wind turbines, cell towers, and pipelines for structural damage, corrosion, or thermal anomalies. The ability to capture close-up imagery without direct human contact significantly reduces risks and operational downtime. This leads to more proactive maintenance and improved asset longevity. The data collected by inspection drones can be processed to create three-dimensional models of structures, allowing engineers to identify defects and plan repairs with greater precision. Thermal cameras can detect heat leaks in buildings or overheating components in industrial machinery, preventing costly failures. For large-scale infrastructure projects, drones can monitor construction progress, ensuring adherence to plans and identifying potential issues early. The efficiency and accuracy of drone-based inspections are transforming industries such as energy, utilities, construction, and transportation, making maintenance operations safer, more efficient, and data-driven. This technology is becoming an indispensable tool for asset managers. Applications. Public safety and emergency response drones are rapidly becoming essential tools for public safety agencies and emergency responders, significantly enhancing their capabilities in critical situations. In search and rescue operations, drones equipped with thermal cameras can quickly locate missing persons in dense foliage, collapsed structures, or at night, drastically reducing search times and increasing survival rates. They can cover vast areas much faster than ground teams, providing an aerial overview of disaster zones. This technology offers a critical advantage when every second counts, allowing responders to deploy resources more effectively and save lives. For law enforcement, drones provide aerial surveillance for crowd control, crime scene investigation, and monitoring dangerous situations, offering officers a safer vantage point. Fire departments utilize drones to assess wildfire spread, identify hotspots, and monitor structural fires, guiding ground crews and improving tactical decision-making. Drones can also deliver essential supplies, such as first aid kits or communication devices, to inaccessible areas during emergencies. Their ability to operate in hazardous environments without risking human lives makes them invaluable assets for enhancing situational awareness and improving response efficiency in a wide range of public safety scenarios. Applications: delivery and logistics. Drone delivery and logistics represent a rapidly emerging application, promising to revolutionize how goods are transported, especially in urban and remote areas. Small autonomous drones are being developed to deliver packages, medical supplies, and food directly to consumers, bypassing traffic congestion and reducing delivery times. This technology offers significant advantages for last-mile delivery, particularly for urgent items or in areas with challenging terrain. Companies are investing heavily in drone delivery systems, aiming to create efficient, environmentally friendly, and highly automated logistics networks. The potential for faster, more flexible delivery options is immense. Challenges in drone delivery include regulatory hurdles, airspace integration, battery life limitations, and payload capacity. However, ongoing advancements in drone autonomy, battery technology, and air traffic management systems are steadily overcoming these obstacles. Drones can also be used for internal logistics within large warehouses or industrial complexes, transporting components or inventory between different sections. This improves operational efficiency and reduces manual labor. As drone technology matures and regulations adapt, drone delivery is poised to become a common sight, transforming the e-commerce and logistics industries and creating new opportunities for rapid, on-demand services. Emerging technologies, AI and autonomy. Artificial intelligence, AI, and increasing autonomy are at the forefront of emerging drone technologies, pushing the boundaries of what drones can achieve. AI algorithms enable drones to make intelligent decisions in real time, such as identifying objects, navigating complex environments, and optimizing flight paths without constant human intervention. Machine learning allows drones to learn from experience, improving their performance over time in tasks like object tracking, anomaly detection, and predictive maintenance. This shift towards greater autonomy reduces the workload on human operators, allowing them to manage multiple drones or focus on higher-level strategic objectives. The integration of AI is making drones smarter and more capable. Fully autonomous drones can execute entire missions from takeoff to landing, including data collection and obstacle avoidance, based on pre-programmed instructions and real-time sensor data. This level of autonomy is critical for applications in dangerous or inaccessible areas, such as inspecting nuclear power plants or exploring remote caves. AI-powered vision systems allow drones to interpret visual information, recognize patterns, and even understand human gestures. As AI continues to advance, drones will become even more sophisticated, capable of complex decision-making, collaborative missions, and adapting to dynamic environments, further expanding their utility and impact across all sectors. Emerging technologies, swarm technology. Drone swarm technology involves the coordinated operation of multiple autonomous drones as a single, intelligent unit. Instead of deploying one drone for a task, a swarm can distribute the workload, perform complex synchronized maneuvers, and cover vast areas much more quickly and efficiently. Each drone in the swarm communicates with others, sharing data and adapting its behavior based on collective intelligence. This technology is particularly promising for applications requiring rapid data collection over large areas, such as mapping disaster zones, large-scale agricultural monitoring, or complex surveillance missions. The redundancy offered by a swarm also means that if one drone fails, others can take over its tasks. The development of drone swarm technology relies heavily on advanced AI, decentralized control systems, and robust communication networks. Challenges include maintaining stable communication between numerous drones, preventing collisions, and ensuring coordinated decision-making in dynamic environments. However, the potential benefits are immense. Swarms can perform tasks that are impossible or impractical for single drones, such as creating dynamic light shows, forming complex aerial structures, or overwhelming an adversary in military applications. As research progresses, drone swarms are expected to play an increasingly significant role in various sectors, offering unparalleled scalability and resilience for complex aerial operations. Future trends and ethical considerations. The future of drone technology is poised for continuous innovation, with several key trends shaping its evolution. Miniaturization will lead to even smaller, more discreet, and highly capable drones for specialized tasks. Increased battery efficiency and alternative power sources, such as hydrogen fuel cells, will extend flight times and range significantly. Greater integration with 5G networks will enable more reliable and faster data transmission, facilitating advanced autonomous operations and real-time control. Furthermore, advancements in sensor technology, including hyperspectral imaging and advanced LiDAR, will provide drones with even richer data collection capabilities. These trends promise to expand drone utility dramatically. Alongside technological advancements, the ethical implications and societal impact of drones require careful consideration. Concerns include privacy invasion due to pervasive aerial surveillance, potential misuse for malicious purposes, and the impact on employment in traditional industries. The development of robust regulatory frameworks, public education, and ethical guidelines are crucial to address these challenges. Striking a balance between innovation and responsible deployment is paramount. Open discussions about data security, accountability for autonomous systems, and the societal acceptance of drones will shape their integration into our daily lives, ensuring that this powerful technology benefits humanity while minimizing potential harms. Ethical design and deployment are key.